Hello, welcome to the fourth session of this series of lectures in this course. So last time we were discussing discussing the complex plane. And with the structures in the complex plane. So we discussed topological structures, topological properties. We discussed open sets, closed sets, compact sets. Alright, so connectedness is still left behind, which we'll discuss in the next session, not today. And then we had algebraic structures. So within this, one was vector space structure. Over R as well as C. Second thing, the field structure. So this was very important as we mentioned in the example. Let's look at the third one, which is, so there is a conjugation closed under conjugation. So what does it mean? It means corresponding to every z complex number there exists z bar. Z which is x plus iy corresponds to this. You have a unique number z bar which is defined as x minus iy in C. This is a map. This is a correspondence, unique, corresponding to each z there exists unique z bar. So this correspondence is called closed under conjugation. So this z bar correspond for every z in C, z bar belongs to C. That's what conjugation means. So z bar is called the conjugate of z. Alright, so the complex plane is closed under conjugation. So it has some properties. So you see, if you multiply z and z bar, which is x plus iy and x minus iy, and you get this x square plus y square, which is nothing but 1 x square. Similarly, you have z plus w whole bar is z bar w bar. You have z bar whole bar is z. So it is x minus iy and then again conjugate. So x minus iy, so it what it does is takes I to minus I, changes I to minus I. Right. And you see, the inverse image of I is minus in the field structure. In the field structure, I inverse is nothing but minus 1. So here it is. Instead of I, you get a minus I, and you put this, define this to be a conjugation. Alright. What's next? Yeah, so z, a complex number will be real if and only z equals Z bar if it is equal to conjugates. So let's look at the geometry. Let's look at the geometry. This is x-axis, this is y-axis. You have this x plus iy, let's say here, x plus iy, which is z, is the point. And corresponding to this, what you do is you put x as fixed as it is and y changes to minus y. So you are reflecting here along the real axis. So this is the point which is z bar x minus iy. Alright? So here it is. So it has a geometry. So conjugation is nothing but the reflection along x-axis. Alright. Now fourth one. Inner product space. So C is of course a vector space over R and C. C has also an inner product structure. We will be interested in the inner product structure with respect to C. So a complex system may be defined the inner product. Let T be a complex vector space and a map is from B cross B to C is called an inner product on B if the following holds. If one, so this, so what should be the properties? Properties is like that. U comma V is V comma U conjugate. So this is not symmetric, this is conjugate symmetric. Next is linearity, which is, let's say, alpha U1 plus beta U2 comma V is nothing but, this is alpha times U1V plus beta times U2 V, and this all is true for all UV, U1, U2, UV. And of course there are more. Three. U comma U is greater than equal to 0 for all U in V, and U equal to 0 and this equal to 0 if and only if U is identically 0. Alright, so this is called positive definiteness. So if V is a vector space, complex vector space, and if the map satisfies this three property, conjugate symmetry, linearity in first variable, this is called linearity in first variable, and this is positive definiteness. If it satisfies these three properties, then we will say this map as inner product. Alright, so example, on C you have ZW bar, and this is the standard inner product. Standard inner product. On C, that we will be considering in this course. Alright. Now let's look at another thing, which is Cauchy-Schwarz inequality. Which most of you know. So Cauchy-Schwarz inequality is, let B be a vector space, P be an inner product space, over R of C, then mod UV is less or equal to square root of UU square root of GV for all U V UV. See, in this case, on C, so this is a remark. On C, Cauchy-Schwarz inequality becomes an equality. Yeah, so maybe you can think of why is this so. That might be interesting. Yeah, so on C, Cauchy-Schwarz becomes an equality, but of course on C over C. So C as a vector space over C, Cauchy-Schwarz inequality becomes an equality. Alright. So this inner product structure will be very important for us to calculate the angle between two vectors or two complex numbers. Yeah. Alright. So this are kind of this few structures, few things. So here Z, Z is, as you see, Z bar. This is mod Z square. And why does this becomes equality? Because this ZW is ZW bar, and we take mod. So this becomes mod Z, mod W by J. Well, here mod Z and mod W. So this is also true. Mod of Z bar is mod Z. Check. So this becomes now square root of Z bar, Z inner product, and square root of W. Alright, so these are the algebraic structure you're talking about, and we'll be exploring more towards this. And next time we'll start with real power series and go to the function. And this inner product and those things will be coming back again in the context when we will discuss Cauchy-Riemann equation and stuff. Okay, thank you.